In this video, we're going to look at an application of a rational function, and we're going to graph that rational function using technology and answer some questions about the function given its graph. So here's the setup. When a drug is injected, the amount of the drug in a person's bloodstream in milligrams per liter after t hours can be modeled by d of t equal to 4t divided by t squared plus 4. We're going to use graphing technology throughout this problem. The first question that we're asked is, what's the drug concentration after 6 hours? Okay, so we can certainly find that algebraically or graphically, right? So if t represents the number of hours, we would be finding d of 6 in this case, right? So we could do that algebraically. They are letting us use technology, so that's easy too. And so part B says, when does the drug reach its maximum concentration in the bloodstream, and what is the maximum concentration? So that tells me that we'll probably be seeing a maximum point. So we'll want to be looking for that maximum. If a patient can't receive another injection until the drug concentration has worn off to 0.5 milligrams per liter, how long must the patient wait to receive the drug again? Okay, so that tells me that we need to maybe put an output value like a y equals 0.5 in there, kind of see where that happens. And then in the long run, what will the drug's concentration be in the bloodstream? So in the long run, that tells me, like, does it have a horizontal asymptote? Like, is it tending towards some value long term? Okay, so let's go to Desmos and graph this. Okay, so I'm going to graph d of t equal to 4t divided by t squared plus 4. That's the function that was given to us, right? Okay, so I see the graph here, and I know that this function is tracking the concentration of a drug in the bloodstream after t hours. So it doesn't make sense for t to be negative, right? So the horizontal axis is representative of time, right? And so I'm just going to drag this over here because I don't even really care about the negative side, as I'm tracking this. I just want to know about that positive side. There were a couple of other things that we wanted to know, right, while I'm in here. We wanted to know what d of 6 was, right? After 6 hours, what's the concentration in the bloodstream? And it's at 0.6 millimeters per liter, right? Okay, so just entering d of 6 into Desmos, it will give that to you. Okay, the other thing that we wanted to know is when can the patient take the drug again, right? It has to wear off to 0.5, right? So I'm going to graph a line right in there at y equal 0.5 so that we know when this graph intersects with that, right? Okay, so what are some really key things that I wanted to know here? I wanted to know the maximum, right? They asked us about that. And then also there are two intersections with 0.5, but at t equals 0, that's when they take the drug, right? So it makes sense that it ramps up in their system and it reaches a maximum and then slowly starts to come back down. And it's right at this point over here on the right at the 7.464, 0.5, that intersection, where the patient could take the drug again, right? So that's some almost 7.5 hours later. So for these questions, let's use this graph to help us out. It says, what is the drug's concentration after 6 hours? Oh, we found that, didn't we? I didn't copy that part off, but Desmos told us that d of 6 is equal to 0.6, right? So that means that the concentration of the drug in the bloodstream. So the concentration of the drug in the bloodstream after 6 hours was 0.6 milligrams per liter. Okay. And then it says, when does the drug reach its maximum concentration in the bloodstream, and what is the maximum concentration? So the maximum point is 2:1, right? We found that we could take that off the graph. Okay, so the 2 represents time, right, in hours. So after 2 hours, we reach a maximum concentration and the Y value is 1, so the maximum concentration is 1 milligram per liter. So let's say that the maximum concentration is 1 milligram per liter after 2 hours, right? Okay, so that's when it reaches a maximum. All right, now if the patient can't receive another injection until the drug concentration has worn off to 0.5 milligrams per liter, how long must the patient wait to receive the drug again? Okay, well, I denoted both of these intersections with 0.5, but really I only want the second one, right? The one that's off to the right there, because they take the drug right at the origin there, right? And obviously the concentration of the drug increases initially very quickly, and then it wears off over time. And so it's that wearing off later on that's when the person would need to take the drug again, right? The person would be able to take the drug again after 7.464 hours, or roughly 7.5 hours. So that's what I would say. The patient must wait 7.5 hours to take the drug again. So in this last question, we're asked, in the long run, what will be the drug's concentration in the bloodstream? If we followed this out further and further and further, so let's go back to Desmos for a moment. Okay, take a look, and I'm just going to start moving with my finger, just moving this further and further out. Notice what's happening, that green line stays consistent at 0.5, but the red line is the function in question, right? And what's happening? It's just getting closer and closer and closer to 0, right? And that makes a lot of sense, because when you take a drug, right, it's going to, there will be a peak in terms of its effectiveness in your bloodstream, and then it's going to decline to 0, right? The drug concentration towards 0 in the long run. Right, which is what we would expect.